The present problem deals with the simulation of a plate heat exchanger called Chevron. Heat exchangers have many industrial applications such as power plants, refineries, process industries, space industries, and so on. The present problem deals with the simulation of a plate heat exchanger called Chevron. In this model, water acts as hot and cold fluid flow in a heat exchanger. The plates between the two flows and all the walls of the heat exchanger are made of aluminum, which is responsible for the heat transfer between the cold water and the hot water flow. The purpose of the present problem is to investigate the heat transfer between two hot and cold fluids through a Chevron plate located between them. The three-dimensional geometry of the present model is designed by Design Modeler software. Since the model is related to the plate type heat exchanger, it consists of two main parts. Hot water flow zone and cold water flow zone. The boundary between these two flow paths is determined by the separator plates or chevron. The non-conformal structured mesh of the present model is carried out by ANSYS meshing software, and the element number is almost equal to 640,000. From the scale mesh section in the general, we can see all the dimensions of all the directions of X, Y, and Z, and also we can check the length unit, that in this simulation the length unit is in centimeter. For example, we can see the length of the Chevron heat exchanger, that is equal to 34 minus 5, that is equal to 29 centimeters. Before setting up the Fluent software for the CFD simulation, we should check the mesh quality. So click on check button and see if it's done or not. In this case, we can see that the mesh quality is alright because it's done. Via the mesh display section in the general, we can display and check all the boundaries, including hot inlet boundary, hot outlet, cold inlet, cold outlet, also all the walls around the Chevron heat exchanger, and also the Chevron plate that has a shadow. Several assumptions are considered for the present simulation. The simulation is a steady state, the solver is pressure-based, and the gravity effect is ignored. Since we are going to investigate and study the heat transfer phenomenon in the CFD simulation for a Chevron heat exchanger as a plate heat exchanger, so the energy equation should be activated. In the viscose model, the standard K epsilon model has been used. That is a two-equation turbulence model that allow the determination of both a turbulent length and time scale by solving two separate transport equations. The standard K epsilon model is in ANSYS Fluent falls within this class of models and has become the workhorse of practical engineering flow calculations in the time since it was proposed. Robustness, economy, and reasonable accuracy for a wide range of turbulence flows explain its popularity in industrial flow and heat transfer simulations. Also, it is a semi-empirical model. The standard K epsilon model is a model based on model transport equations for the turbulence kinetic energy K and its dissipation rate epsilon. The model transport equation for K is derived from the exact equation, while the model transport equation for epsilon was obtained using physical reasoning in the derivation of the K epsilon model. The assumption is that the flow is fully turbulent and the effect of molecular viscosity are negligible. The standard K epsilon model is therefore valid only for fully turbulent flows. In the near wall treatment option, we select the standard wall function. Because if the K epsilon turbulence model is used like in this simulation, it is not possible to simulate flow vortex near the walls. So a wall function must be defined, that is a standard wall function for this simulation, to investigate the fluid behavior near the wall. The liquid and the fluid that is going to be used in this CFD simulation and as the main flow for the heat exchanger is liquid water. So we define all the material properties in the material tab. And all the walls of the heat exchanger and also the Chevron plate are assumed to be aluminum as the default solid material of the Fluent software. Before investigating the boundary conditions, we should check the sail zone condition. There are two separated zones of cold part and the hot part. Both of them are the fluid type, and the material for the fluid type is defined as water liquid. As it is obvious, there are two inlets and two outlets for the CFD simulation. Two inlets for hot and cold water inlets, and two outlets for, again, hot and cold outlets. The cold inlet water temperature is equal to 283.15 degrees of Kelvin. And the velocity magnitude is equal to 0.25 meter per second, and the specification of the velocity is the magnitude and normal to the boundary. By the way, the inlet types for both inlets are velocity inlet. Also, the pressure outlet boundary condition type is set and selected for both outlets of cold and hot. The outlet gauge pressure is assumed to be equal to 0. That means that it's atmospheric pressure. The hot inlet temperature is 60 degrees more than cold inlet temperature, that is equal to 343.15. and the velocity is equal to the cold velocity. All the walls surrounding the heat exchanger, the plate heat exchanger, are insulated and adiabatic, so the heat flux thermal condition is set for all the walls, and also the heat flux is equal to 0 because it's an adiabatic wall. Also, all the walls surrounding the Chevron plate heat exchanger assumed to be a stationary wall and no slip. Finally, we should set the last boundary condition in this section that is related to the plate. The plate is the Chevron plate. It's a stationary wall and no slip. The thermal condition should be set as a coupled wall. The material of the coupled wall is assumed to be aluminium, and the wall thickness, the Chevron plate thickness, is equal to 0.5 centimeter. Since the Chevron plate is assumed to be a coupled wall, there are two different zones in both sides of the Chevron plate, so it's a coupled wall. And because of that, a shadow is defined for the plate. The simple algorithm in the solution methods section uses a relationship between velocity and pressure corrections to enforce mass conservation and to obtain the pressure field. Also, the pressure velocity coupling scheme controls the manner in which pressure and velocity are updated. When the pressure-based solver is used, the scheme can be either segregated, like simple, that pressure and velocity are updated separately, or coupled, that the pressure and velocity are updated simultaneously. ANSYS Fluent provides the following segregated types of algorithms like simple, simple C, piezo, and fractional step or FSM. In general, segregated methods like simple that has been chosen in the CFD simulation are faster per iteration, while the couple algorithm usually requires fewer iterations to converge. For setting under relaxation factors, we should say that the pressure-based solver uses under relaxation of equations to control the update of computed variables at each iteration. In ANSYS Fluent, the default under relaxation parameters for all variables are set to values that are near optimal for the largest possible number of cases. These values are suitable for many problems, but for some particularly nonlinear problems, for example, some turbulent flows or high Rayleigh number, natural convection problems, it is prudent to reduce the under relaxation factors initially. It is good practice to begin calculation using the default under relaxation factors. If the residuals continue to increase after the first 4 or 5 iterations, you should reduce the under relaxation factors. Occasionally, you may make changes in the under relaxation factors and resume your calculation, only to find that the residuals begin to increase. This often results from increasing the under relaxation factors too much. A cautious approach is to save a data file before making any change to the under relaxation factors and to give the solution algorithm a few iterations to adjust to the new parameters. Typically, an increase in the under relaxation factors bring about a slight increase in the residuals, but these increases usually disappear as the solution progresses. If the residuals jumped by a few orders of magnitude, you should consider halting the calculation and returning to the last good data file saved. You can use the residual monitors dialog box to control the residual information that Fluent software reports. In the equations section, the residual option indicates the name of each variable for which residual information is available. And the monitor indicates whether or not the residuals for each variable are to be monitored. You can toggle monitoring on and off for each variable by turning the corresponding checkbox in the monitor list on or off. The check convergence option indicates whether or not the convergence of each variable is to be monitored. If convergence is being monitored, the solution will stop automatically when each variables meet its specified convergence criterion. You can check convergence only for variables for which you are monitoring residuals. You can toggle convergence checking on and off for each variable by turning the corresponding checkbox in the check convergent list on or off. And finally, the absolute criteria or relative criteria shows the residual value for which the solution of each variable will be considered to be converged. To set this value, manually enter the new value in the corresponding absolute criteria field. And that's it. We use the hybrid initialization because there are two inlets and two outlets in this CFD simulation. For the CFD simulations that there are more than one inlet and outlets, and there are some difference in the direction of the fluid to be enter the zone, and for the outlet of the zones, when there are some complicated path lines, it's better to use the hybrid initialization, like in the CFD simulation of the Chevron Plate Heat Exchanger. We just click on the initialization button and go to the run calculation section. We set the number of iteration equal to 2500. It seems enough for the iteration of this CFD simulation, and after that we just click on the calculate button to start the calculation. At the end of the solution process, we are able to obtain all the desired contours, vectors, path line, and also reports. For this case, we are going to define a plane that is Z constant and pass through the Chevron heat exchanger, and it's placed on the center of the heat exchanger. So we should do the following process. The dimensions of the heat exchanger along the z-axis is between 5 and 34 centimeters, that the center line would be equal to, the ISO value would be equal to 19.5 centimeter. Then we can reach to all the two-dimensional contours that we require on the defined plane Z center. We also can define and specify every plane in every direction, just like this issue. Here is the two-dimensional pressure contour. This is the velocity contour on the Z center plane, that it's obvious that near the chevron plates and near the heat exchanger walls the velocity is almost zero. And finally we can see the two-dimensional temperature contour, and it is obvious that in the upper zone there is hot fluid, hot water, and in the bottom zone it's cold water, and we can see the temperature distribution range. Also, all other desired two-dimensional contours are going to be obtained in this section. One of the most important parameters and results that should be checked in the plate heat exchangers like this simulation of Chevron is the wall fluxes. Wall or Chevron plate total surface heat flux could be obtained this way. Through the report section, by selecting the surface integral and identifying the area weighted average in the report type, we are able to obtain all the reports by just specifying the field variable. For example, suppose that you are going to obtain the pressure drop in the hot or cold zone. The pressure drop in the cold zone is equal to 679 Pascal. Also, we can check and see the outlet temperature from the cold outlet and also hot outlet. Here is the summaries of the problem definition and problem solving steps in the table as a review. To benefit from Master CFD services including simulation, consultation, and training, contact our experts via info@mastercfd.com. Hope you enjoy.